Welcome to the 6th video in special relativity. In this video we will be looking at the Lorentz transforms. So we have our familiar situation of a rocket ship moving with a velocity u in the positive x direction relative to a man. And what we want to try and do is to be able to describe the position of an object in the man's reference frame, so that's x, y, z and t in space-time coordinates, relative to that position in the rocket's reference frame. So that's x dash, y dash, z dash and t dash in space-time coordinates. So we use the dash to indicate the coordinates or the reference frame itself that's moving with the relative velocity. And so we know a couple of things about how we're going to do this. We know that at relativistic speeds we use the Lorentz transform, and that Lorentz assumed that the transform has the form that x dash is equal to gamma times x minus ut. And the condition on that transform is that at Newtonian speeds, so at the kinds of speeds we're used to dealing with, where v is much less than c, or where v on c is approximately 0, then that factor gamma needs to reduce down to 1 so that we get our Galilean transform of x dash is equal to x minus ut. So we write our two transforms as this. We say that the position x dash of Hardy, who is in the rocket, relative to Laurel, so Hardy's position as viewed by Laurel, is x dash is equal to gamma times x minus ut, and vice versa for Laurel's position as viewed by Hardy. So we'll start with these two equations. So we have our Lorentz transforms, these two equations, to describe relative positions in space between the two reference frames. And since they both depend on time, we can use those equations to find the Lorentz transform for our position in time. So we'll start with our equation of Laurel's position relative to Hardy, x is equal to gamma times x dash plus ut dash. And we'll substitute into it our formula for x dash. When we expand that and simplify it down, we find that t dash is equal to gamma times t plus x on v divided times the factor 1 minus gamma squared divided by gamma squared. And if we do the same procedure, but starting with the other equation, we get the equivalent equation for our time t equal to gamma times t dash minus x dash on v times the same factor, 1 minus gamma squared on gamma squared. So now we have our Lorentz transforms for our position, our x position, so the position of the dimension moving with the relative velocity, and our time. Since our y and z positions in space are not moving with any relative velocity, they are equivalent in both reference frames. So just to point out, the Lorentz transforms, they relate the position and time of a single event in some frame S to the position and time in another frame S dash. So they're dealing only with the location of an object in space-time. They are not dealing with a time interval. And so to be able to use these equations properly, we're missing a fairly important piece of information, which is we'd like to know what gamma is. And so to find gamma, we know that these two sets of equations must be equivalent. That is, we know that under this Lorentz transform, the rules governing physics in both reference frames must be the same. So what we do is we'll look at a point in time when both our reference frames, so our S and our S dash reference frames, blue and red reference frames, are at the same location in both time and space, in space-time. And at that exact point in time, at the position of x equals 0, y equals 0, and z equals 0, although I've not shown the three-dimensional axis here for simplicity, there is a flash of light. And then we look at that event, that flash of light, in those two reference frames at some time t later. So that flash of light, the wavefront of that light is expanding in a spherical wave at the speed of light. And once again, I've only shown, and I'm only doing the two-dimensional calculation here for simplicity. So since we're working in 2 dimensions, that flash of light is expanding as a circle in 2 dimensions. So in both reference frames, if we look at a position on that circumference, so on that initial wavefront of the light, we know that it's described by the position vector r, and we know that r squared is equal to x squared plus y squared by our Pythagoras. We also know that light has travelled in some time t, that light has travelled a distance equal to the speed of light times that time. So we know that r is equal to ct. So ct is the hypotenuse of our position triangle. So that gives us the equation in both reference frames that x squared plus y squared is equal to ct squared. And in the red reference frame, x dash squared plus y dash squared is equal to ct dash squared. And once again, because we know that the laws of physics must be the same in both reference frames, we know that these two equations must be equivalent. So what we do to find gamma is that we start with our equation x dash squared plus y dash squared is equal to ct dash squared, and we substitute into that equation our equations for x dash and t dash, so our Lorentz transform equations. When we do that, that gives us an equation for x, y and t in terms of our Lorentz factor gamma, and that equation for x, y and t must be the same as x squared plus y squared equal to ct squared. And then solving or simplifying down those equations, we can find an expression for gamma. And I won't do the working here because it will detract from the point of this video. But when we do the working, we find that gamma is equal to 1 divided by the square root of 1 minus v squared on c squared, where v is the relative velocity of our second reference frame, so of our s dash reference frame. So now we have our equation for gamma. So this is the Lorentz factor gamma, and this is the factor that we use in every single Lorentz transform. So now we have an equation for gamma. We can use it to simplify our Lorentz transforms for time by simplifying that factor that appears in both of 1 minus gamma squared divided by gamma squared. So we find our expression for gamma squared equal to c squared divided by c squared minus v squared, and we substitute that in to each equation. So substituting into our t dash equation, we find that t dash is equal to gamma times t minus xv on c squared, which is a much nicer expression to work with than the first one, and similarly into our second equation, and we get the equivalent equation for t. And so the last thing we need to do is we need to check that our gamma that we found actually satisfies the requirements of the Lorentz transform, which is that at low speeds, then our Lorentz transform approaches our Galilean transform. So we need to find that our gamma approaches 1. So as our velocity is approaching 0, the velocity component of the Lorentz transform, v squared on c squared, is also approaching 0. And so therefore our gamma, which is equal to 1 divided by the square root of 1 minus v squared on c squared, is equal to 1 divided by the square root of 1. So gamma approaches 1. So our equation for gamma satisfies the requirements of the Lorentz transform, and we can now happily use these 8 equations to transform between our positions in space-time. I will add one more equation to this set, and that's the equations that show us time dilation. So that's the equations for the Lorentz transform of a time interval. So in our previous video, we saw that delta t dash is equal to delta t times the square root of 1 minus v squared on c squared. And looking at our value for gamma, we can see that that actually equals delta t divided by gamma. And we get a similar equation for delta t.